So far in this presentation, we've been talking about the effects of magnetic fields. In this section, we're going to start learning about the sources of magnetic fields. If you haven't already watched the Veritasium video on sources of magnetic fields, please stop this video now and watch that video first, and then come back here when you're done.
Welcome back. Hopefully by now you've had a chance to observe the Veritasium video about the origins of the magnetic force. You should have seen in that video that the magnetic force can result from moving charges. It is just the electric force as seen from a reference frame where the charges are in motion relative to the reference frame. So you may have actually experienced this yourselves if you've ever had a chance to make an electromagnet. They're not that hard to make. You just take an iron nail, wrap it in some wire, and then touch the ends of the wire to the terminal of a battery, and voila, you have a magnet. We're going to do the same thing here, except instead of using a nail, I'm just going to use a lot of wire. And I've wrapped the wire around these four posts of this device. This is called a tangent galvanometer. And as you can see, there's some wire wrapped in a square frame around the posts of the tangent galvanometer. And there's a little platform here that is a place where I can put a compass. And what we're going to do in a moment is we're going to see what happens when we put a compass in a platform on the tangent galvanometer. Now, the compass aligns itself with the magnetic field. I don't want to count the magnetic field of the Earth if I'm trying to find out what magnetic field is caused by my moving currents in my wire. So I'm going to align my compass with the plane of the loops of wire, if you will. And that way, I know what the result of this is going to be. The magnetic field is going to be pointing a different way, and so any deflection of my compass then can be explained as being caused by the external magnetic field caused by the current flowing in these wires. So let's go ahead and turn on my current, and we'll see what happens here. Okay, just take my word for it, the compass is deflected. No, I wouldn't do that to you. I'm going to lay the tangent galvanometer on its side, and we're going to see how the magnetic field of the wires here deflects the direction that the compass is pointing.
So here I've turned the apparatus on its side so we can get an idea of the magnetic field caused mainly by any current flowing in these wires over here. I'll turn some current on, but before I do that, I want to point out that right now, with no current flowing, the compass needle is aligned with the white notch on the housing of the compass, and I'm going to try to keep that notch pointed in the same direction the whole time. So if we see a difference between where that white notch is and where the compass needle is pointing, we'll know that there's some extra magnetic field in addition to the magnetic field of the Earth, as shown by the compass. Now I'll turn the current on, and right now there's about 2.25 amp current flowing in these wires, which means the effective current is much more than that because there's a number of wires going past here. So if there is a magnetic field over here, it either is very weak or it is in the same direction as the compass needle was pointing because of the magnetic field of the Earth. Let's see what happens when we move our compass to a different position now. Again, I'm going to try to keep the top of the compass needle pointed in or compass housing pointed in the same direction. And now we can see that there is some deflection. It is as if the combination of the magnetic field of the wires and the magnetic field of the Earth has caused the net magnetic field to be pointing more in this direction. If I keep my compass pointed in the same direction, my compass housing, but I come over here instead, well, now we see that the magnetic field, the net magnetic field, kind of points in this direction. And if I take my compass and put it inside of the coil here, we can see that it looks like the magnetic field is pointing kind of opposite the way the magnetic field was pointing originally, just caused by the Earth.
Okay, so now that we've seen that, let's go ahead and see if we can get a measurement of exactly how strong this magnetic field is. Now, when we're doing this, I'm going to have my tangent galvanometer, I'm going to have my compass, I should say, placed in the middle of my tangent galvanometer, and we're going to detect the magnetic field of the coil by taking the net deflection that we get from the magnetic field's deflection, which should be in a coil of wire like this, it should be basically straight out of the frame. And then the magnetic field of the Earth, which I have aligned with the plane of the frame. And so what we're going to get is we're going to get two magnetic fields, and we're going to be able to measure the direction of the resultant. And that direction alone will be sufficient for us to tell how strong the magnetic field is of this plane compared to the magnetic field of the Earth. And I have to make sure this is carefully lined up. I'm going to make sure that the direction of the plane of wire is lined up with the magnetic field of the Earth, and that this is right smack dab in the middle there, and it is. And I'm going to turn on my current, and let's just take some readings at different current values. So we'll bring the current down to here. We'll have it at 1.00 amps. And right now, the deflection of my compass is, well, it's going from 360, so it's going, that's 30 degrees, 30, 40, 35, 40, 45. So right now we're getting a 45 degree deflection of my compass needle. That is to say, the angle between the net magnetic field and the north, if you will, is 45 degrees. Let's change it to 1.5. That's close enough. 1.53, and the compass reading is, that's 30, that's 300. So it looks like it is 55 right now. Looks like it is 55 degrees is the angle between the north and the overall magnetic field here. Let's go ahead and switch it to a larger current. There is 2.00 amps. And my compass reading is, let's see, that's 65. Looks like it's 65. It's 5 degrees past the 300 degree mark. So it looks like it's 65 degrees. And we can see if we can get maybe one more at 2.5. Two point 2.47 amps. And the deflection is 60, looks like that's 270. No, let's see, that's 60. Looks like it is 70 degrees. 70 degrees is my deflection there. So we'll analyze this data, and we'll see if we can get an estimate of how strongly the magnetic field produced by my current depends on the current.
Before we begin the quantitative analysis of the lab that we just saw, let's talk a little bit about what we saw as far as the direction of the magnetic field produced by the current carrying wires. When I was holding the compass next to the segment of the tangent galvanometer, you could see that the magnetic field seemed to point, it changes direction as you moved around the wire. The direction of the magnetic field takes around a long straight current carrying wire follows a circular pattern around that wire. So it is both perpendicular to the wire itself, and it is perpendicular to a line drawn from the wire to where you're trying to measure the field. So if you were to graph magnetic field lines, remember lines of a field show the direction of the field at any given point. If you were to graph those magnetic field lines, what you'd end up with is concentric circles, showing the direction of the field tangent to those circles at any given point. The way to remember the direction of the magnetic field, if your current is going up, then as you see in the picture here, the magnetic field would curl around it, the magnetic field lines would curl around the current carrying wire. So if you were to take your fingers of your right hand and your thumb of your right hand and let your thumb point in the direction that the current is flowing in the wire, your fingers of your right hand would naturally curl in the direction that gives you the direction that the magnetic field lines curl around the wire. Remember, magnetic field lines don't actually show you the magnetic field vectors. They just give you the direction of the magnetic field at any given point, which is going to be tangent to that line. Here is my lab notebook page from the tangent galvanometer lab. I do these, and I put the pictures of my lab notebooks in here just to kind of show you what I kind of expect you to be doing when you're doing your labs. You'll notice that I have the date on there. You'll notice that I have just a sketch of the lab apparatus. This may be the one that I'm going to use in my final lab report, or it could be just a sketch that would help remind me of how we did the lab. But you should always make a sketch of your apparatus because you might have questions later about how you did the lab. And then I did a little diagram there that is, we're going to show you later more about that diagram. It's how we're going to analyze the lab. And then I have my data table showing the raw measurements that we made. So let's talk about how we're going to do the analysis, the quantitative analysis, to find the strength of the magnetic field in using the data that we got from this lab. So we actually have two magnetic fields present here. We have the magnetic field of the Earth. In my diagram here, I'm going to draw it pointing up. So up would indicate north. Broadly speaking, north is the direction the magnetic field was pointing. And then we have the magnetic field produced by the current in the wires. Now, I happen to know, we haven't actually proven this yet, but the direction of the magnetic field by a loop of wire like that is going to be perpendicular to the plane of the loop. So if I orient my loop so that the plane of the loop is pointing in the direction of the magnetic field of the Earth, then the direction perpendicular to the plane of the loop will point in the direction of the current. And if we have two perpendicular vectors and they are making a net magnetic field, well, that's my net magnetic field. And the direction of that is going to be sufficient to tell us what the magnetic field caused by the current was if we know the magnetic field of the Earth. Because these vectors form a right triangle, I can just measure that angle in there. And if I know that angle, well, that angle, according to right angle geometry, the tangent of that angle must be equal to the magnitude of the magnetic field produced by the current divided by the magnetic field produced by the Earth. And we can rewrite this like this. So if we know the local strength of the Earth's magnetic field there, without any added field from the current, and we measure those angles, we can come up with the approximate magnetic field strength caused by the current. So I had to look up in a map available online what the magnetic field strength was approximately here in the Houston area. I found out that the magnetic field strength is about half of a Gauss, 0.5 Gauss, which means that it's 0.00005 Tesla. Taking that, then we can calculate the magnetic field produced by the current just by taking the tangent of the angle that we found times that magnetic field strength of the Earth. And there you see the data from our lab. And I've also included an extra column there, which is the calculated magnetic field of the current. So in order to determine the relationship between the magnetic field produced by the current and the current itself, I graphed the magnetic field of the current on the vertical axis and the current itself on the horizontal axis. It came up with a fairly linear graph. Gives you some constant confidence that we're on the right track here. And if we ignore the intercept, we get the formula that the magnetic field of the current is equal to 6.0 times 10 to the minus 5 Teslas per ampere times the current. Now, if we ignore that intercept, and it is a somewhat significant intercept, then we could say that the strength of the magnetic field produced by the current in the wire is proportional to the current. Now, I don't believe the intercept is actually so small as to be negligible. It may indicate a real thing. Perhaps, and this is just a rough guess, it represents magnetic field that I didn't quite zero out by positioning the compass correctly. If the compass is positioned so that the magnetic field of the Earth is directly along the plane of the tangent galvanometer, so the tangent galvanometer has to be positioned that way as well, then you should have no other magnetic field when the current is zero. But because there is going to be an intercept here, in fact, it's going to be a negative intercept that might indicate a problem with how the compass was placed. But I believe we can be confident in saying that apparently the magnetic field does depend directly on the amount of current that is producing that field. So between the video and the demonstrations that we viewed and our little experiment here, we can arrive at some principles surrounding the sources of magnetic fields. Magnetic fields are caused by currents, or more generally, just moving electric charge. And the strength of the magnetic field does seem to depend on the magnitude of the current, or the rate at which the charge is moving, if you're talking about individual charges. And the magnetic field direction does follow a right-hand rule as well. We will see more about this in the next section. But it is definitely perpendicular to the charge flow. When the charges were flowing up in the wires, we saw a magnetic field get produced in the plane of the tangent galvanometer. And it's also perpendicular to the vector from where the charges are located to where the field is being measured. And we'll talk more about that in the next section. And as I roughly indicated with our little demonstration with the tangent galvanometer, the magnetic field lines surrounding a long straight wire are concentric circles. That is to say, at any given location around a long straight wire, the magnetic field direction is tangent to a circle around that wire.